Hello everyone. In this video, we'll see why series motors can never be started at no load. So first see the construction of a series motor. So if I draw the construction of a series motor, then there is a series field winding, and this is the armature, and this is positive voltage and this is negative. Okay, this is series field, and this is armature. So the series field is connected in series with the armature. This is connected in series with the armature. Now for the DC motor, what you can write, like flux phi proportional to Ia in series field current is equal to armature current. Because of this, we can write, because of series field current is equal to armature current armature current. So the back EMF EV is equal to K phi N. So back EMF EV is equal to K phi N, and the torque T proportional to phi Ia. We can write that is T proportional to that Ia square, as we know that phi proportional to Ia. So as we know that this phi proportional to Ia, so we can write T torque is proportional to Ia square. Okay. Now we can write the speed equation. So we can write speed N is equal to V minus Eb by K phi. So N is equal to V minus Eb by K phi. Now at no load condition, at no load condition, we know that at no load the mechanical load is 0. So that is one mechanical load is 0. Mechanical load is 0. Then the armature current Ia becomes very small. Then Ia is very small. Ia is very small. So only enough to overcome losses. So therefore series field current is also very small. So series field current is also very small. Now what are the other condition? Flux phi becomes very small. So flux phi very small, and back EMF EB is equal to K phi N becomes very small. This is also very small, near about 0. So that is near about 0. So from the speed equation, what we can write, as we know that N is equal to V minus EB by K phi. This is the speed equation. So this what we can write, V by very small number, very small number. So this means speed becomes extremely high. So what we can say from this, what we can write, speed becomes extremely high, as this term is very small number. So that's why this speed will be very high. Now we'll understand why this speed becomes extremely high, or what you can say that why this runway speed occur. Why we can say this, why this runway speed occur. Why this runway speed occur at no load? What we know, at no load Ia is small. So if Ia is, so what we can write, small phi. Because of that Ia small, okay, we can write in this load small Ia, so phi small. So then to balance the supply voltage V, to balance the supply voltage V, the motor speed N, the motor speed N increase sharply. So because of that, eb is equal to k. So eb is equal to k pi n rises. But at n increases, but as n increases, but as n increases, only a very small increase in phi. Small increase in phi. So cause n to rise to a dangerously high value. So this because of that n is dangerously high value. That means there is no natural limit to this speed. Okay, now if we see the speed armature current characteristics, speed versus armature current characteristics. So we'll understand, like in the y-axis is speed, and in the x-axis, that is the armature current so if we draw the graph, that graph will be like this. So from this graph, what we can understand, so this is the zero, means where ia is equal to 0. So in this position, we can see that is speed is near about infinite. So at no load, where ia near about 0, speed tends to becomes infinitely high. So speed infinitely high. So this is the like speed and armature current characteristics. So what we can say, at no load, series motor takes very small current. So finally, what we can write, at no load, series motor takes very small current, very small current, very small flux, very small flux. So because of that small current, flux is very small. So as flux is very small, negligible back EMF. Then to balance the supply voltage, so in this condition, to balance the supply voltage, to balance the speed rises to a dangerously high value. Speed rises dangerously high value. Okay, thank you.